We're going to start this video off with a similar example to one that we did or ended with in the previous video, but we're going to do limit as x approaches negative infinity of this rational function. So same technique, we're going to divide out each term by the highest exponent. See what happens. And then remember, anything that's left with a variable and an exponent on the denominator goes to 0. So in this situation, all of these little fractions that are left here go to 0, and we end up getting the limit is equal to 1 over 0. That means we need to check. There's no horizontal asymptote. And we're going to check if it goes to positive or negative infinity. So we do our check. Now, the only thing we have to check here is because it's going to negative infinity, we want to check the negative aspect. So go back to the beginning. Again, really focus in on the leading terms. What would happen if I plugged in a really large negative number to those leading terms? Oops. A large negative number, or any negative number to the fifth, is going to come out negative. And then a negative number squared is going to be positive. So this would end up approaching negative infinity. Now, just because the limit approaches negative infinity does not necessarily mean that its limit will be negative infinity in these situations, which is why you want to do the check. Because if I had thrown in a negative sign in front here, that would entirely change what would happen. So always important to do the check and then decide, are we approaching positive or negative infinity? Now I want to take a look at one special case to kind of wrap up this video. And we're going to look at some limits where we really can't look at what's happening as they approach infinity unless we do something to change them around. So I would put limit as x approaches infinity of x squared minus x. We can't write, this is not a real number. We're plugging in as big of a number as we can. That's not even possible to do. What's happening as we're approaching infinity in this polynomial function, or really quadratic function, we can't just think about what would happen if we plugged in a really big number to each part. So something that we talked about in one of our first lessons algebraically is we could potentially separate this into limit as x approaches infinity of one part minus the other part. The problem is those limits are not real numbers. So if you did this, you would get infinity minus infinity, which is 0. Infinity is not a real number, so that limit law cannot be applied to this. And the reason being, infinity is not a real number. Instead, you would have to think about the function as a whole. What happens to the function x squared minus x as it approaches infinity? This function itself is going to infinity. So you have to kind of envision your graph and what's happening here as we're going to positive infinity. It is also going to positive infinity. There's really no real analytic way to do that, but there is on this special case example that we're going to do here. So in this one, it's the same scenario. We have square root of x squared plus 1 minus x. Radical function combined with a linear function. Either way, you can't really plug in infinity. You can't separate those functions out. What we can do is we can make this into a rational function. You might be thinking, why the heck would we do that? Make something that's not a fraction already into a fraction. It does allow us to then do some of the things or techniques that we were using before with dividing out the highest variable on the numerator and denominator. So the way we're going to do that is we're going to multiply by the conjugate. We used this technique before, and we're going to include now a denominator so that we can do our dividing. The only reason we're able to divide out each term is because we're doing the exact same thing to the numerator and denominator on those previous examples. You would not be able to do that unless you already had a fraction. So we're creating the fraction scenario here. We'll get x squared plus 1 minus x squared over the square root of x squared plus 1 plus x. And we get limit as x approaches infinity of 1 over square root of x squared plus 1 plus x. Now here's where it gets a little tricky if it didn't feel tricky already. We want to divide out the highest exponent. If you notice inside here, if I were to take the square root of x squared, that would also be equivalent to x. So we're technically going to divide everything by x. In this scenario, which means inside the radical, we'll divide by x squared, because that's what's equivalent up here. And outside the radical, we're going to divide by x. So you just need to do that increase or decrease depending on which part you are in the function. So we'll divide by x for on the outside of the radical. For we're on the inside, anything on the inside, we'll divide by x squared. And then we'll get 1 over x over square root of 1 plus 1 over x squared plus 1. Same rules apply as before. Any of the fraction pieces will go to 0, or anything left with a variable in the denominator. So we end up getting 0 over the square root of 1 plus 1. We don't get 0 over 0. We do end up getting 0 over 2, which is equal to 0. You may not always get this type of question equal to 0, but that does happen frequently, so don't let that freak you out. But the key with this is knowing that you have to do this first step and get it into fraction form. You can't do the dividing on each of the terms unless it's in a fraction. So if you started with that in the first step, that would not be correct algebra that you would be doing. All right, so that wraps up our second video with a couple special examples. Now you'll have a chance to practice some of these limits as x goes to infinity.